The quality of service parameters, which form the basis of QoS routing, can be grouped into two main classes: the additive and the non-additive matrix. In this module, we'll explore the non-additive matrix. First, we'll understand what do we mean by non-additiveness. Then we'll see how this is applied in the context of routing. And then we'll investigate various aspects of non-additive matrix. The book explores additive and non-additive matrix at length with regards to routing and multiplexes. Non-additive matrix can be defined as the routing matrix which cannot be linearly summed up. It means if we have, let's say, 3 hops or 3 links in a path, this metric is not going to be simply multiplied with a factor of 3 in case the cost is the same, or these cannot be represented as the summation sign. So if we want to determine the overall end-to-end impact of non-additive matrix, we have to do it through another way. As an instance, let's consider bandwidth. If we have the same scenario in which we have 3 links and individual bandwidths of these 3 links are the same, say 10 megabits per second, then we surely cannot say that the end-to-end bandwidth is 30 megabits per second. Instead, what we'll assume is that if the flow requires d units of bandwidth and each link has a certain capacity of bandwidth, then the available link bandwidth along the path would be the minimum of all. And if the requirement is, say, d bandwidth units per second, in that case, each link on that path should support at least d. Non-additive matrices are tricky in the sense that they have to be treated differently, manipulated differently, but there are also some aspects which emerge depending upon which non-additive matrix we are talking about. In this case, if we consider bandwidth, we'll understand that bandwidth is something that we cannot be sure of, because as we talk, the bandwidth occupancy could increase or could reduce. What if the bandwidth requirement is not met, although the source and destination path does exist? In such case, when we prune out the links below the bandwidth requirement, we'll eventually prune out the whole network and the source and destination would be isolated. If more than one paths exist and each path is fulfilling the requirement of minimum bandwidth, with which path to choose turns out to be yet another level of decision making. The bandwidth measurement, if it is done frequently, would involve active probe packets and discovery, which would have its own overhead. Likewise, more frequent bandwidth discovery means high accuracy, but low accuracy is achieved if the bandwidth is not determined frequently. So this trade-off is also important. Then the bandwidth measurement is not always accurate, because by the time, as I said, measurements are made, the bandwidths might have as well changed. So the solution is to look at the bandwidth requirement in a probabilistic sense. That is, depending upon the past behavior and bandwidth availability of these paths, we can look at bandwidth based, which is a non-additive metric, routing protocol to choose a path with the highest probability of having D units along all the segments or links of that path.